Welcome back. This is a course on fundamentals of micro and nanofabrication. This is a follow-up lecture that discusses details of substrates. So, in part 1 of the substrate, we looked at how exactly what sort of materials are available in the market, what are its characteristics, what are its specifications. I very briefly and very generally introduced the concept of crystal growth, specifically Czochralski method of growth. In this part of the lecture, we will go into a little more details. This will be a little more technically involved part where we will focus on a couple of interesting technical concepts such as supersaturation, distribution coefficient, etc. So, let us get started. So, in order to understand crystal growth, the best example, the most relatable example is probably to understand is something that we are all familiar with, which is dissolution of glucose or sugar in water. So, if you take water and try to dissolve glucose in it, you will actually form a saturated solution at 91 grams. So, that is the solubility of glucose in water. So, let us look at this process. Strictly speaking, crystal growth is not a solution, but the concepts travel. Okay. So, let us get started. So, supposing you take a water solution at 25 degrees C and you put say 100 grams of glucose in it. Initially, not all of the glucose will dissolve because the system is not under equilibrium. So, it is slowly, you can imagine that it is slowly dissolving, but it is not completely dissolved yet. So, this system is not under equilibrium, and what you actually have is at any given point in time, say if you have 5 grams of glucose dissolved, you can call this an unsaturated solution. Okay. Now, if you give it long enough time, ultimately the system will reach equilibrium, which is when the the solubility limit of glucose in water is reached, which is 91 grams. At that point, the 9 grams that is left over is just going to sit at the bottom of the cup because well, it cannot go into the solution anymore. So, now this solution is at equilibrium, and what you have is a saturated solution. Okay. Now, imagine you heat this solution up to 50 degrees C. So, if you remember the basics of chemistry, when you heat a solution, the solubility actually goes up, and it goes up to an extent where the 9 grams that was sitting at the bottom would also dissolve away. So, all 100 grams of glucose is now in water, but what you have is an unsaturated solution because the solubility of glucose at 50 degrees C is even more than 100 grams. Okay. So, the system is at equilibrium. Now, supposing we cool this system down back to 25 degrees C. Now, remember the equilibrium at 25 degrees C is that 91 grams of glucose is soluble, 9 grams is sitting at the bottom. But right now you have a system which has 100 grams of glucose in the water. So, now it needs to make a transition from this state into its equilibrium, but that transition will not happen instantaneously, it will take a little time. So, if I were to suddenly cool this solution from 50 to 25 degrees C, at least initially I will have this unstable system where there is 100 grams of sugar in the water solution, right. This is what is called a supersaturated solution. This system is not under equilibrium, and if you allow it a nucleation event, what that is we will discuss in a minute, then the excess glucose will precipitate out. Because it is precipitating out from a solution, the process is often slow. And if you can actually through some tricks make it very slow, you can actually get a crystalline glucose precipitate that precipitates out from the solution, so that it again has 91 grams in the water and 9 grams is your precipitate. So, you are going from a supersaturated solution to a saturated solution. So, the concept of supersaturation is that simple. It is simply that through some trick you have now made the system go beyond its equilibrium value, beyond its capacity to carry that material. Now, this the process that we just looked at is actually maybe familiar to some of you. This is how we make mishery or rock candy. If you do not know what I mean, maybe this picture will jog your memory, but you can actually create these very fancy looking candies, which are essentially crystals of sugar with some color in it in this case. And this is the process by which you make them. What you are essentially doing is you are doing crystal growth. You are starting with the polycrystalline sugar, right, which is the granulated sugar that you can buy in the market. You are dissolving it in water, and by this process of supersaturation to saturation, you are actually extracting larger grains. Now, these are not single crystal, but they are still larger sized. Now, if you were to do this very, very precisely, maybe you can even get a single crystal of sugar. Fundamentally, that is what we are trying to achieve when we are trying to make silicon, single crystal silicon using Czochralski method. Here is, by the way, a QR code of how you make rock candy at home. Those of you who are experimentally inclined may want to try it one day. It's fun. Now, what we are doing in silicon is slightly different, as in that we are not dissolving silicon in a solution like water. Instead, we are melting it. But the fundamental concept remains the same. We are going to create a supersaturation. How do we achieve supersaturation in a melt? Well, we freeze it to beyond its melting point, right? So, in silicon, we will take a melt and we will start cooling it down, and we will bring it below the melting point of silicon. So, the liquid of silicon or the melt of silicon that is below its melting point is now in supersaturation. So, now it is unhappy. The system wants to quickly become solid, and by controlling that process, in this case by incorporating a seed, we are hoping to grow single crystal of silicon. So, here example, here is a GIF where this water has been super cooled, and then you introduce a seed of ice, and that seed of ice suddenly creates a nucleation event which makes the whole of the water crystallize into a solid. This is what Czochralski method is trying to do. The only difference is that in this case the seed is polycrystalline and it's uncontrolled. So, the crystal of ice that you are forming is also polycrystalline and uncontrolled. In a Czochralski method, this whole process is much more precisely controlled, and because the seed has a single grain, you grow a single crystalline ingot. Okay. So, this is what very fundamentally supersaturation does for you. However, an added advantage of this is we get something called zone refining. The solid that we make is purer than the liquid that we started with. So, there is a purification that comes for free while we are doing crystal growth. Okay. Why that happens is the subject of the next few slides. In order to fully appreciate and understand what zone refining is, you need to know what binary phase diagrams are. This is a materials concept. If you are not familiar with, here is optional extra reading that you can do. This is not part of the course curricula, so we will not quiz you on it, but those of you who really want to understand crystal growth should understand phase diagrams. Okay. So, here is a video, QR code that you can access. The things to focus on in that video is to understand what is a unitary and a binary phase diagram, the lever rule, and binary phase diagrams with limited and unlimited solubility. Okay. So, these are concepts that are covered there. If you are interested, you can read up it. Once again, this is optional reading, you do not have to do this. Moving on. A quick primer on what is a eutectic binary phase diagram. Okay. So, typically a phase diagram looks something like this. A eutectic phase diagram looks something like this. Here what you are looking at is a plot of temperature versus concentration. Okay. So, this side, supposing this is a binary phase diagram between a material A and B. So, on the right is 100% pure B, on the left is 100% pure A, and in the middle are alloy compositions between that 100% pure A and 100% pure B. Now, in our case, this could be an example of we starting with pure, we want pure silicon, but we do not have pure silicon, we have certain impurities. So, we have an alloy of impurity and silicon. So, we are probably somewhere here, right. So, if you have 99.99% pure silicon, you are very close to this origin, but not exactly at 0, right. So, supposing that impurity is iron. So, what you would then look at is the binary phase diagram between silicon and iron, where the left hand side is pure silicon, the right hand side is pure iron, and in the middle is all the alloys, all the transition alloys in between. So, the starting point is very close to this origin, but not exactly there. The second thing is we are going from melt to solid. So, we are essentially reducing the temperature. So, we start with liquid, which is this liquidus L region, and we come down from this liquid into below the liquidus line. At this portion, we form a two-phase system. Okay. So, it is not like the system instantly cools, it forms a mixture of a liquid and a solid. If we cool down even further, we reach the solidus line. This is the point at which you form a homogeneous solid. Okay. Now, so in when you are doing Czochralski method or doing crystal growth from a melt to a solid, the area of interest in a phase diagram is this portion where you are starting from a liquid and going to a solid through this transition region. Okay. So, now what I will do is in the next slide I will just focus on this rectangle. Okay. Now, the important concept that you might want to remember for the next slide, even if you do not understand phase diagrams, is the system does not like to remain in this L plus alpha region. Okay. So, the system is happy in the above liquidus, the system is happy below solidus, system is unhappy in this region. So, in this region the material will phase segregate, it will try to form, it will try to reach the solidus line or the liquidus line, it will try to not remain in this A region. Okay. So, if you just remember this, you will be fine for the next slide. So, what I have done is I have zoomed into that region. So, if you zoom into that region, again you see this liquidus line, you see the solidus line, you see this yellow region, which is the region where the system does not like to remain because it has two phases in it. Above it you form a single liquid phase, below it you form a single solid phase. Now, let us start with the material that has one impurity of concentration C naught. So, once again you are not at 0, you are certain concentration of C naught and you are starting from a liquid, and then you are reducing the temperature to freeze it. Okay. So, you start at that point and then you reduce the temperature. So, you come down that line and you reach the liquidus. Now, remember the system does not like to remain in this yellow region. So, then what it does phase segregation. It forms a material that it forms two materials, one at the liquidus line, one at the solidus line. So, this material is what is solid. So, this is the material that has frozen, and the concentration of impurities in this frozen material, if you look at this line, is this, right, which is lower than what you started with. Okay. So, the presence of this yellow region ensures that when you freeze a material with an impurity concentration C naught, the solid that you form will be K C naught, where K is less than 1. K here, by the way, is a distribution coefficient. We will come to that in the next slide. Of course, you are not done. You can continue this process. Now, you can again take this impurity concentration and freeze it again, and then it will go down, and once again it is unhappy in the yellow region. So, it will again phase segregate. It will form a phase, it will go below the solidus line to form a material with lower concentration of impurity and form a material that is at the liquidus line. Now, impurity cannot be created or destroyed. So, the average impurity concentration remains the same. So, where do the impurities go? So, impurities go into the liquid phase. So, you see the liquid that you have formed actually has higher impurity concentration than the solid that you formed. So, what has happened is the average remains the same, but when you solidify from a melt, the impurity concentration in the solid is at a lower concentration than the impurity concentration in the liquid. So, in some sense the impurity wants to remain in the melt more than it wants to remain in the solid, and that tendency of the impurity is what allows us to form a purer solid. Okay. This process is essentially called zone refining. You can continue to do this ad nauseum, and every time you would continuously form a purer version of the solid than what you started. So, the solid is purer, the liquid becomes impurer, right. Another thing that you should notice here is that as we are progressing in this, the initial solid that you formed is the purest solid that you can form, but the subsequent solids that you would form would be slightly more impure than the solid that you formed in the start. Why is this happening? Because you see all the impurities are getting more and more concentrated into the liquid. So, the impurity concentration is liquid keeps increasing. So, the solid that you form from that liquid also is slightly more impure. This is what causes a certain gradient in the impurities that in the solid that you have formed. Okay. If this is not very obvious right now, wait for 2 slides, we will go over this once again. Okay. Now, to simplify the mathematics of this process, we can define something called the distribution coefficient, which simply is a constant that tells us that if you were to freeze a solid from a liquid, how much impurity will remain in the solid and how much impurity will remain in the liquid. So, this is the concentration in the solid Cs and the concentration in the liquid Cl. So, this K is different for each impurity. Here is an example for different impurities and their Ks. So, things that are extremely bad for electronics are things like iron. Okay. So, they typically have a distribution coefficient of 10 to the power minus 6. So, once again, what is distribution coefficient? It is the ratio of impurity in the solid versus liquid. So, a very, very low K of minus 6 essentially means that the probability of an impurity staying in the melt is 10 to the power 6 times higher than the probability of it coming into the solid. So, that tells you that you can essentially, by just melting and refreezing, you can purify your silicon of iron impurities by 10 power 6 times. Okay. So, that is your purification ratio. Another extremely bad defect to have is gold, and gold again has an extremely low distribution coefficient of 10 power minus 5, which is extremely good, which allows you to form purify gold impurities by melting and refreezing. But that is not true of all impurities. There are certain impurities like arsenic, phosphorus, boron that tend to have distribution coefficients that are relatively high. So, they will still refine themselves, but not as much as iron and gold. Thankfully, these impurities are also dopants, right. So, this allows you to dope the material. So, the solid still has the dopant while still being able to purify the really bad metals such as gold and iron. Now, one thing to note is this, that the metallic impurities distribution coefficient being very low and the dopant concentration being high is a complete luck, right. We got lucky with silicon. This is one of the reasons why silicon is so popular, that we can create doped silicon with relative ease while at the same time getting extremely pure silicon. Right. So, if for a different material this may not have been true. Finally, a comment about the K does not always have to remain less than 1. If your phase diagram is not eutectic but peritectic, you can actually get a situation where the impurity wants to remain in the solid and not in the liquid. So, if that is the case, then the distribution coefficient will be more than 1. That is an example of oxygen in silicon. So, this is the reason why the oxygen concentration in the silicon ingot is 10 power 17, 10 power 18. Even though the dopant and the impurity concentrations are much lower. Right. Now, here is to help you visualize the process as a function of distance. Okay. So, I sort of hinted at it earlier, but let us look at what is happening. So, again imagine you have a melt and you have a seed, you are rotating the seed and you are slowly pulling it out. At time 0 in the liquid, you have a impurity concentration of C naught. At this point, the very first dx material that will actually freeze out will have a concentration of K into Cl. If K is less than 1, then this value is less than C naught, which is the fundamental of zone refining. The material that you have formed is purer than what is the melt that you started with. Next. So, what has happened? All the impurities have been ejected from the solid and into the liquid. Now, if the melt remains homogeneous by mixing and other ways, now what you have done is you have created a melt that is slightly more impure than what it was at T equal to 0. So, it is slightly more than C naught. What this would mean is the next material that would solidify would actually see a slightly higher concentration of impurities. So, the more impure melt will also a more impure solid. So, the subsequent solid will also be slightly more impure than the solid that was formed at T equal to 0. And if this process continues, what you can sort of see is as you solidify more and more of the material as you go down this x axis, the concentration of impurities in the solid would also increase. So, this is what this plot represents. I urge you to go and do the math yourself, but if you actually solve the differential equation of this process, you can actually calculate what the concentration of impurities in the solid is as a function of x. So, this is a very easy 1D problem to solve. Here is a formula, but do not worry, we will not quiz you on this formula. The thing to notice, however, is that there is a change in concentration of the solid as you go from x equal to 0 to x equal to 1. This is a reason why you cannot specify a single impurity concentration. You need to always give a band, all right, because the concentration will change in the ingot as you start from the top of the ingot and go to the bottom of the ingot. Okay. So, that change essentially means that you always need to specify a band of impurities. You cannot tell a crystal grower that give me this precise impurity, because that can never be achieved. Okay. The second thing to notice in this is that it really depends on the distribution coefficient. So, things that have high distribution coefficients, for example, dopants tend to be 0.1, show a relatively shallow change, but things that have high distribution coefficient, for example, this is 10 power minus 2, show a very sharp profile. So, you see there is very little impurity at this end, very high impurity at the edge, which is the consequence, which is the fundamental of zone refining. So, when things like gold and iron that you are really trying to remove, very little of the gold and iron will be in the first half, most of the gold and iron will be in the last half. Okay, okay, moving on. Now, one of the things that I assumed, and this is a little bit of the detail, is I assumed equilibrium. So, when the impurity was ejected from solid and entered the melt, I assumed that the melt would become homogeneous instantly. Of course, this does not realistically happen. What is realistically going to happen is all the impurities that were ejected from the solid will accumulate near the solid. So, the concentration of impurities near the solid will actually be higher than the concentration of impurities deep in the melt. Now, this is a kinetic effect. So, you need to be a little more careful. Practically what that means is the effective distribution coefficient that you would observe in your process will be a little higher than what theory tells you. Okay. So, this is the net effect because of this piling up effect. Alright, that is enough of the details and equations. Finally, you will get an ingot. The thing to remember is that ingot will have a pure end and a impure end. This is the starting point, this is the ending point. The starting point will have very few impurities, right. It will tend to be less doped. The ending point will have more impurities and it will tend to be highly doped. Where will you get your wafer from? Will you get it from the starting end or will you get it from the other end is what is called the grade of the wafer. So, the prime refers to the fact that I am getting my wafer from this first half where impurity concentrations are much lower, and a mechanical or a test grade wafer probably will come from this end where the wafer impurity concentrations are higher. So, for electronics you always want to get wafer from this edge. Okay. And the second thing to remember is dopant concentration is never constant in an ingot, it varies. It is the doping is lower at the first half, higher in the second half. That is why you can never give a precise value of doping. Okay. So, those are the two things we have learned from all of this. This is another optional extra reading, we are not going to quiz you on it, this is just for those of you who are interested. The eutectic phase diagram that we just discussed and the crystal growth that we just discussed is actually the same concept that is behind the growth of nanowires. So, there is a whole field of where people grow single crystalline nanowires using gold or silver. How do they do that? You can read up on your own. Here is a reference of a good paper that goes into the details, but fundamentally it is the same crystal growth problem that we just discussed. Moving on. Of course, reality is always a little more complicated than the simple model, 1D model that I just discussed with you. Here is what an actual crystal growth system looks like. I will just highlight some of the important features. Number one, you notice that the seed and the shaft lift and rotation. If you remember in the first lecture I mentioned that the area of the wafer is decided by the by the speed at which you pull the seed and the thermal management, right. So, this is a very important aspect of crystal growth. If you want to get a certain diameter of an ingot, this needs to be very precisely controlled, and these days it is often done by computers. Then there is of course a sensor, so that the computer can actually get a feedback on the diameter. So, it actively sees what the diameter is and changes the rate of pulling. Okay. The second thing is, you see this upper housing isolation valves. These are what allow you to make sure the system is sealed and the oxygen from the atmosphere doesn't get in. It also what keeps the system sealed so that heat doesn't leave out, because again, if the heat leaves out, then your area becomes smaller. And then there is a control power supply that actually measures this temperature of the melt, which is very important to maintain uniform area, etc. Now, if you try to do the same process of CZ and try to make gallium arsenide, which is the most common 3,5 material we get, we are not as lucky as we are in silicon. It's remarkably hard. And while there are several reasons why this is remarkably hard, the major reason is the following. When you have a melted gallium arsenide, arsenic tends to leave the gallium arsenide. The arsenic tends to evaporate out. Arsenic is a low temperature element. In order to prevent escape of arsenic, typically you need to add a capping agent. Often that capping agent is boron oxide or something like that. Now, this solves the problem of arsenic leaving. So, the stoichiometry of the melt remains the same. However, it adds a problem, and that problem is that the thermal management becomes remarkably hard. Heat is lost at this boron oxide interface. The area is very hard to, it becomes very hard to control the area. So, you end up making ingots that look like this. So, there is because of this capping layer, there is a thermal instability, and the thermal instability leads to an instability in the area. So, the area of the ingot keeps changing. So, you form these wavy sort of ingots, and that too not of extremely high quality. This is the reason why gallium arsenide often is not made using Czochralski silicon. There is a competing method that we will discuss in the next slide that is often used. The other way of making ingots is something called a float zone method. The idea of a float zone method fundamentally is the same, it's just that the hardware is a little different. So, the way it happens is the melt never touches another solid, so it is not inside a crucible. You start with a polycrystalline ingot. This could be a piece of the polysilicon, for example, or it could also be a piece of CZ silicon that you have already made. Okay. Then you introduce an RF coil around this. Now, this RF coil will cause localized heating. So, you are not melting the full ingot, you are causing localized heating. This localized heating will melt a small portion, and that melted portion will fall because of gravity and fall through the RF coil and then fall down and then resolidify, because the heating is localized. As soon as it passes the heated zone, it resolidifies. So, if you slowly move this RF coil from the bottom to the top, you in one or from the top to the bottom, you would actually crystallize the material from top to bottom. So, this is what the cartoon looks like, this is what an actual system is looking like. So, you are seeing that this RF coil is going from top to bottom, and as it is going, it is melting and refreezing the silicon. At its core, once again you are doing the same thing, but the only major difference between this and CZ is that there is no seed, rather the seed is useful only at the first start. After that, the material that you have crystallized itself becomes the seed for the subsequent silicon. And the second most important part is because of localized heating, the whole melt is not melting, only a small portion of it is melting. I leave you to think about in detail why, but one great advantage of float zone silicon over CZ silicon is that you are able to achieve much lower resistivities. Okay, it is a much more effective method at removing impurities. Why? The reason for that is in the math. If you do the differential equation solution of this process, the fact that not all of the impurities are accessible, only a localized amount of impurities are accessible, is one reason why this happens. Okay. However, there is a problem. This method is much slower than CZ silicon and hence much more expensive. So, you would only do this for cases where you really want very high quality silicon. Again, I would not go into the math of it too much, but once again you can make these plots where you are looking at the concentration as a function of distance, and here also, just like in CZ, there is a variation. It does not give you uniform concentration. You typically get purer material at the front end, impurer material at the back end, and how much more impurer will also depend upon the distribution coefficient. Smaller distribution coefficient cause more of a gradient, larger distribution coefficient cause less of a gradient. another interesting aspect of float zone silicon is you can continuously do this process again and again, and every single time you do it, you will actually get purer and purer material. So you can do this multiple passes, as they call it. So a single pass material will, for example, form this blue line, but if you do a second pass, it will be purer than the blue line. If you do a third pass, it will be more pure. And using this, you can actually arbitrarily increase the amount of purity of the material that you are forming. This again means that for niche application where you want extremely pure silicon, a float zone is much more interesting. If you try to do the CZ silicon, it would not work because you are melting the whole boule. The third method is actually gradient freeze method. Here again the concept remains the same, but the hardware is slightly different. What you actually do is you create a melt in a sealed ampule, and the ampule is lowered in an oven whose temperature changes from bottom to top. So going from bottom to top, the temperature is different, and as this ampule is lowered in this furnace, it starts crystallizing at the lower end, and this crystallization front progresses until the whole melt is crystallized. This is called the Bridgman-Stoke-Barker technique. Without going into details, I'll just inform you that this gives lower dislocation density than the CZ method, and this gives you much better quality gallium arsenide wafer. So for gallium arsenide, this is the method of choice. It's not CZ silicon, it's not float zone silicon. It's not CZ or float zone methods of crystal growth. Overall, what is the impact of impurities? So the bulk silicon has an atomic density of around 10 to the power 22 centimeter cube. Okay. So when you say that an impurity of 10 to the power 14 centimeter cube or an impurity of 10 to the power 12 centimeter cube, you are implying that that material is 1 in 10 to the power 8 or 10 ppb or 99.999999% pure. Okay. So just to give you context what 10 to the power 14 or what 10 to the power 12 actually means. Through this process of crystal growth, through the three techniques that we mentioned, which is CZ silicon, float zone silicon, and a vertical gradient method, you can actually get silicon that is 10 to the power 14 to 10 to the power 12 pure. Okay. So group 3 impurities are less than 10 to the power 14 or less than 10 to the power 12. Heavy metals are often less than 10 to the power 12. Oxygen is a little higher. Remember, the distribution coefficient of oxygen was more than 1. This is the reason. And the carbon is less than 10 to the power 15. So by and large, through this process of crystal growth, you are achieving a reduction in impurities by an order or 2 orders of magnitude, and that is a side effect of crystal growth, and that is because of this is what is called zone refining. Finally, you have this pure ingot, but this has these wavy patterns on the top. You grind them out. After grinding them out, you cut them into wafers, and finally you also ground out something called flats. So flats are these flat regions that are made in the cylinder. So for example, this is what a typical p-type 111 wafer looks like, and the 111 p-type wafer has one major flat. So you see this major flat? So this flat tells you that this is p-type 111 wafer. If this was a p-type 100 wafer, it will actually have 2 flats. If it was an n-type 100 wafer, it will have 2 flats that are 180 degrees. So depending upon where the flat is, you can actually tell the doping and the orientation of the wafers. So this is a standard. So during this grinding process, they also cut out these flats. After that, the wafers are sawed or the ingot is sawed into wafers. But during the sawing process, you always create damage at the surface. So in order to remove that damage, typically you etch around 20 microns off the surface of the wafer. This is typically done chemically using a variety of baths. Some of them are acidic in nature, some of them are basic in nature. After this is done, you still have a relatively rough surface. So in order to smooth it to an optical finish, you then do grinding. This is very similar equipment to what is used in lens making or in optical component making, where they also get smooth process through polishing. So this is a typical polishing system. You take your wafer, you put some weight on top, and that silicon wafer is rotated on a bed. That bed is made of some hard material. There is a slurry. Slurry is also made from some is made of particles of very hard material. So it functions as an abrasive, and by just very slow etching and very slow grinding, you smoothen out the surface. Here are some details of what the typical recipes look like. I would not expect you to remember these, just the concept that we are using some slurry, some aluminum oxide based or a cerium oxide based slurry, which is very hard material, and using it to slowly etch the surface. We remove around 25 to 30 microns from the top, and what is left is a very smooth surface whose flatness is around 5 to 10 micron and RMS roughness is less than 1 nanometer. Okay. You can do this on one side, you can do this on both sides depending upon whether you want a single side or double side polished wafer. One final note, not all wafers need to be single crystalline. There is a market, in fact in solar there is a market for multi-crystalline silicon where you do not care about single crystalline. Here the system becomes much more simple. You simply take a melt and you do a vertical freeze, and there is no seed, so you do not form a single crystal, but you form multi-crystalline wafers, wafers that have several grains. These wafers tend to have grain boundaries which make them electronically inferior but cheaper. So in some cases, for example solar cells, this is commonly done. Finally, we come back to the specifications we started with. Now some of those specifications will make a lot more sense to you. For example, float zone silicon typically would mean it can be very highly resistive, it can have very low concentration of impurities. So if that is what you need, you should get float zone silicon. What does prime mean? Prime simply means that we are getting the wafer from the front end of the ingot where the impurities tend to be the lowest. Whether you should use 100 or 111 or 110 really depends upon the application you want. It's easier to make 111, it is harder to make 110, so you pay for the extra effort if your application requires it. Then what is test and mechanical grade? This is the wafer that you get from the other end of the ingot that probably has more impurities. So if you do not care about the electronic properties and just the mechanical properties of silicon, maybe this is good enough for you. For even lower grade, you can go to a microcrystalline, and in certain applications you want to maybe polish both the sides, which is what double side polished wafer is. With that, we come to the end of this series on substrates. In the next lecture, we will discuss cleaning technologies. So you may have noticed there was so much effort put into purifying the material, in creating a material with very low impurity. That would be no good or no use if we do not maintain that purity. So how do you maintain that purity? The subject of the next lecture. Join you back then. Thank you.